I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs, identifying diseases like leukemia from a simple drop of blood, even in our own homes, and finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses, and a learner, discovering new strategies from complex games. I am even the composer of the music you're hearing. I am AI.
And I am Umid Akhmedov from Advanced Analytics team at IT. In this session, I'll go and talk about artificial intelligence. But before I proceed, I would like to give some safety instructions. If alarm goes off, please keep calm and proceed through the doors with exit signs and make your way to the master points. Furthermore, in this age of digitalization, remember to lock your computers when you leave the desk. Do not open suspicious emails and do not share your passwords. And now back to our topic. We'll go through what artificial intelligence is, why we need to be using it, and how have we been implementing it at Ørsted so far. But first thing first, what is artificial intelligence? AI is a branch of computer science that studies creation of systems that can replicate intelligence processes by machines, especially computer systems. But in order to understand what an artificial intelligence is, let's imagine an opposite, the natural intelligence. The best representative of a natural intelligence is a human. So humans have eyes, and they can see and process the visual scenery, and this corresponds to something called computer vision. Computer vision captures and analyzes visual information using a camera or digital signal processing, and it's not bound by biology, so it can be programmed to see, for example, even through walls. It's used in a range of applications from face recognition to signature identification and maybe even medical image analysis. Humans can navigate through the environment and do mechanical and repetitive movements. This corresponds to a field of robotics. And robots are often used to perform tasks that are difficult for humans to perform or perform it consistently. They are used in assembly lines for production or, for example, move large objects in space. Robots are using artificial intelligence techniques to adapt to the environment, but we will see some more examples on that later. Humans can speak and listen So they can also communicate through language. And machines can organize our speech. The machines can recognize our speech, and they can read and write as well, which is broadly known as the field of natural language processing, NLP. It's processing of human language by a computer program. One of the older and best known examples of NLP is spam detection, which looks at the subject and the text of an email and decides if it's junk or not. Current applications of natural language processing include text translation, sentiment analysis, and speech recognition. Humans have the ability to detect patterns, such as grouping similar objects. Machines can concentrate even more and recognize patterns in the data because they can use more data and dimensions. This is field of machine learning because it allows machines to act without programming. There are a lot of different algorithms for machine learning, but usually they are brought together into following major groups. The first one is supervised learning. Here we feed millions of examples of input data to machine with their labels, then let the machine figure out whether the new input falls under the category, this or that category. Supervised learning tasks find pattern where we have a data set or we have a data set of right answers to learn from. So this is typically applied for classification problems. Then comes the unsupervised learning. Unlike supervised learning, unsupervised learning searches for patterns where we don't have a set of right answers. This may be because the right answers are not observable or infeasible to obtain, or maybe even given problem doesn't even have the right answer per se. To make a parallel, the combined processing of all of the above, so human eye and speech and movement and learning, all of these happen in the human brain. The human brain is a network of neurons, and we use these to learn things. If we can replicate the function of the human brain, we might be able to get cognitive capabilities in machines. Neural networks is an information processing concept inspired by the brain activity. And deep learning is probably one of the most used subsets of machine learning that is, in very simple terms, can be thought of as mimicking the activity in layers of neurons in the neocortex, which is the rinky 80% of the brain we use to think in our brain, right? To summarize, the artificial intelligence is really a set of techniques that help machines and computers mimic human behavior. And I like to have an analogy with the Russian Matryoshka doll, where artificial intelligence is at the highest level. It's the vision, it's the intelligent, the smart thing. How this smart thing becomes smart is under the hood. It's the next layer. It's the machine learning doll, which are the set of techniques used to make that device smart by learning from large amounts of data. Then there is further subset of algorithms or techniques called deep learning, which is machine learning technique inspired by a human brain. I think that AI technology, especially deep learning, has now advanced to the point where we see a surprisingly clear way for it to transform every major industry. Now, despite all that hype about artificial intelligence, it turns out that 99% of economic value created by AI today is through one type of AI, which is learning A to B, or input to output mappings. For example, it's getting really good at inputting a picture and outputting something like, is it a cat or not? So let's imagine a situation where I want to buy a product, but I don't have money for that. So I want to apply for a loan, and I come to the bank. The bank checks out my data, like income and expenses and age and family, and that's my input data. And it at the output returns yes or no answer to the question whether I repay the loan or not. Once I got the money, I go out and search the internet for that product, where the online advertisers based on my user data try to predict whether I click the ad or not. And this is almost a core business for research engines, search engines like Google and Baidu and Facebook and Twitter. So let's assume that I click the ad, then using my previous transaction data and time I've spent on each on each side of the website and clicks history, the whole algorithm goes on to predict whether I buy the product. And the same logic goes if I am existing customer, yet the output would be if I cancel my contract with the company or not. Let's go to extremes and imagine that I bought the self-driving car that also happens to be full of sensors, and that needs to predict the turn of the wheel, or to suspend or not, to accelerate or not, etc. So just final remark on this discussion. It looks like simply automating things or sequence of yes and no decisions that a typical person could take in under 1 second is adding already a lot of value today. So for example, if we take a simple recognition pattern, a typical person would identify whether the image is a face in under 1 second. However, the machine should combine several layers. Understand first how the patterns of the pixels are combined, identify the basic lines, then put together those basic lines into forms, and then try to figure out whether those objects are combined in something meaningful, for example, a face. And if it's a match, then of course it will return you an output of 1. The natural question is, how come deep learning is driving a lot of the recent excitement in the artificial intelligence area? After all, it's that simple, and basic concepts have been around for many decades. Why are neural networks and deep learning taking off just now? The answer is simple. We saw digitalization of society for the past 20 years, and for many industries, we collect a lot of data, more and more data coming from smartphones, computers, and digital activities. So if we could plot the amount of data on the x-axis and the output, the quality or performance on the y-axis, then the graph would show that more traditional AI algorithms like logistic regression or support vector machines performed no better with the increase of amount of data. More recent developments in training neural networks showed constant growth in performance. As with any technology and new development, there come some issues. We should expect that we would need to address the bias issues. We need to address the level of trust of our AI models. This is especially important in life-critical systems, and you have probably seen the incident with Volvo Uber in US last Sunday. And in that case, who is to blame if the machine has done an error? Is it me who created the model, or is it you who tested it, or is it that company that sold it to others? Do we always need to explain what the machines has done and why? And who decides how machines identify the level of information that we need to be consuming? So once we look at those issues, it's easy to speculate whether it's appropriate to call it intelligence at all. After all, it's still primitive. So far, I've heard of many alternative names for AI acronym. One of them is amazing innovation. The other is augmented intelligence. This one we will not tell about because it was just Google. I tend to refer to it as to applied innovation, because with the development of processing power of the computers and storage prices going down, it became possible to use AI techniques in everyday life. While it might take more than 10 years to create a full-scale, broad AI, the narrow AI is, as we have mentioned in previous slides, are applied in everyday lives. So the other day I was booking a flight with our travel department, and they booked a flight and picked the right dietary meal for me on the flight. For a moment I thought that they guessed by my name or by my face, It turned out that there was no mystery, and I just forgot that I once many years ago entered it into my profile. But nevertheless, the only fact that we don't exclude it from the equation is already explaining how applicable AI became in our everyday life. Indeed, Netflix is using it to recommend movies to us every day. Facebook, Google are using it to optimize search and many other things that we don't even know of. Amazon is using it to sell more products. And PayPal has cut its false alarm rate by half using the deep learning techniques. So while these giants are spending billions of dollars on AI, small startups are emerging like mushrooms after the rain. There are more than 4,000 startups building their products on the back of artificial intelligence, and their average valuation is approximately 30 million Danish krone each. This is actually double as much compared to only a couple of years ago. In Northwest Europe, 22% of the businesses are investing in artificial intelligence, and this number is expected to grow to 85% by 2020. And please note that this is not a scary thing, as only 8% of the businesses are seeing AI as a direct replacement for people, while more than 30% believe that the goal is to assist human decision making to deliver better experiences. While 80% believe that robotics, advanced analytics, IoT will predominate business models in the next 5 years, 16% say it's already today. And I strongly believe that Ørsted is among these 16%. Such an adoption pattern shows a growing gap between adopters and those who wait. Automakers use AI to develop self-driving cars and improve operations, while financial services firms are more likely to use it in customer experience related functions. Early evidence suggests that artificial intelligence can deliver real value to serious adopters and can be a powerful force for disruption. It is documented that early adopters that combine strong digital capability with proactive strategies have actually higher profit margins and expect the performance gap with other firms to widen in the future. The 4 areas across the value chain where artificial intelligence can create value is through, for example, smarter R&D or optimized production and maintenance, a better marketing, and better user experiences. And according to the survey by Gartner, by 2019, deep learning will provide best-in-class performance for demand, fraud, and failure prediction. And 2019 is basically 9 months, which poses the question: are we ready? So you have probably seen Dungeons and Dragons working full speed towards building preventive analytics functions in their everyday work. And amazing work the guys are doing is a topic in itself, so it will probably be a subject for a separate session. For today's talk, I wanted to show you a couple of examples from other parts of the business at Ørsted. And the first one is actually related to that fraud detection that we mentioned in previous slides. Market abuse is something that is becoming very high on the agenda for the regulators. Before I continue explaining what that solution that we've built was, I want to give a short example about what the market abuse is. And in order to do that, I'll just break it down to a very simple terms. So imagine I have bought a stock of an unknown firm in Silicon Valley for $1 each, and then I go out and spread the rumor that this is a company that is going to make a fortune within the next year due to the breakthrough in the R&D. Once some investors believe in the story and start buying the stock from me, I do additional trades with someone I know to increase the price and send a signal to the stocks and to the market that the stock is growing. Finally, I sell 100 shares at $1, 300 shares at $5, and 600 shares at $10. In the end, I make 760% on my $1,000 investment, but this is potentially could be any product and not only stocks, and this is not allowed. This was just a simple example, and there are more than 15 scenarios one could manipulate the market with. The regulators are so serious about this that if they catch anyone doing this, they could fine us or fine the one who made the abuse by 25% of the revenue. And this is revenue, not profit. So back in 2016, it turned out that energy companies like ourselves should also comply with this regulation. And in the case of energy markets, where some of the gas contracts are priced based on the index of some components, the traders of an energy company can potentially enter a manipulative activity to affect the prices of an index and hence get favorable delivery prices on gas. So the compliance office started to search for a product that would help the company to comply with this regulation. And most of the companies came with a price tag of approximately 6 million krona a year in the license plus the implementation cost. The problem was that the regulation came only with the general guidelines of forbidden intent rather than clear step-by-step instruction on what to detect. But we tried, and we ran a POC, and we showed that there is a potential to build ourselves a cheaper and better solution in the time frame that an off-the-shelf product would take to implement. So we had to translate the regulation into formal algorithms that would allow the system to detect the fraud based on the data that we receive from the trading systems, the transaction storage, and the news. We have even prepared the system to extract the traders' conversations at the time when the abuse took place. Why this is amazing? Simply because there is only one person who needs to surveil over 20 traders across 2 business units trading in more than 120 instruments. This is more than 2 million rows of data from one source per day, and there are more than 3 sources to come. And we can also be proud that we are actually one of the first ones in Europe on energy markets who managed to implement such a solution. And expert systems like this would evolve just like the trader's mind in the future. These days, traders are not coming from business schools, they are coming from physics or mathematics schools, and they are technology aware, and there are more and more machines trading on the market. Thus, especially in the energy markets where probably this hasn't been a trend so far. So we see a future potential in expanding the capabilities of the system with more features and functions that technology would allow in order to detect not only the human fraud but also the potential fraudulent algorithms of the machines. Let me show you how easy it became to write an algorithm these days. So we actually wrote the code for we took a stock of Ørsted, and we imagined that we had $100,000 and to invest and simulate what would we earn if we had a machine to do it for us. And you can see here that based on the simulation data, the data is true, the model is simulating it. We could actually earn that much on this much of an investment. This specific algorithm is not fraudulent, but as soon as we have the ability to code it like that, then we have the opportunity also to do something wrong and mistakenly make a fraud. This is the reason why AI fraud detection algorithms will get even more attention in the coming years. But let's hear Torben, who worked with us in order to build this system. Let's hear what he has to say.
In this specific case, we built a system that surveys for potential manipulative behavior by Ørsted traders in relation to all trades, all orders in the marketplace. We're talking about millions of data records each day and quite sophisticated behavioral patterns. Human surveillance cannot be used for such a task simply because the amount of data and the complexity is too high. It could be interesting to run the MAR system real time to let it predict possible manipulative behavior even before it happens, based on learnings from previous manipulation. Another important aspect of market surveillance is to detect possible collusion between traders. That could be in writing or it could be voice. The ability to detect collusion between traders in different languages and maybe even coded language is a very difficult task, and we need machines for that. I think it's a maturity journey. You kind of have to deserve the right to build these machines by showing you can do it. On the other hand, the business must embrace the idea and show confidence in IT that they can solve these kind of tasks. I think that's needed to take us the next step, not just to talk about machines and robots, but to actually develop them and use them.
Thank you, Torben. I mentioned that the demand prediction is another interesting area AI and artificial intelligence could be applicable in. Have you asked yourself ever, how do we find, sorry, here, yes, how do we find next markets to enter? And there is a complex combination of more than 100 factors that should give an optimal result in order for us to bet on a given entry. And there is a team of dedicated analysts working on those cases. Together with the Hyperspace Lab, we have built a pilot product. We have enabled the team to find out the sentiment of a given market towards a topic that could be interesting for them. And this is just only one factor, and we're not telling exactly which word combinations is that due to security reasons. But the system itself is like it listens to the Twitter feed and reads all the tweets and the messages, and then tries to figure out on this given topic what is the sentiment. Is it positive, negative, or neutral? The funny thing is that in this pilot we were up against IBM Watson's crawling machine, and we are proud to say that we could achieve even better results with open source technologies. Well, if not better, then at least at par. But let the brain behind this speak himself and show you a demo. Please meet Mark Skov-Madsen, the guy who beat IBM Watson.
Okay, thank you, Umit, for that nice introduction. So I'm from Jutland, and I feel I would like to go back to Jutland now because that was some introduction. Okay, so I was given the opportunity, and thank you everybody who's out there. I was given the opportunity to give a tangible introduction to machine learning and AI. So I would like to do that. Yeah. So first of all, I'll start out by, machine learning is already here. So it's in the news. You've heard about it. It's with Tesla. They're using it for self-driving cars, but it's actually also here in Ørsted. Umit already gave some examples, and I will start out by giving a small example from the Hyperspace Lab. Okay, so what you see here is actually an application that we built for wind power, for market development. So market development in wind power, they're looking at the different markets that we're interested in, and they look at a lot of information, and one of the sources of data or information that they're not using today is actually Twitter. So we work together with them and try to help them build an application for monitoring tweets. So that's what you can see here. So on the right we have the different tweets that are related to offshore wind. That's the area of interest for the market developers, and they would like that. So we help them build a traditional integration to Twitter. But then they say, okay, I want to filter this. So I'm a market developer. I'm not looking at all markets. I'm only looking at selected markets. That's my job. So please help me filter this. So we needed to label all the tweets with a relevant market for the market developer. And in the old days, we would just build a rule somehow, finding out from the tweet which market to assign or label it with. But instead we found it interesting to build a machine learning algorithm, because it's a little bit complicated. Because when we looked at the tweets, we looked at it and say, okay, should I label it with the nationality of the person who tweeted this? Well, not really, because this person, he could be at a conference in Brazil, so that could be his location. And that might be more interesting if it's a conference in Brazil. But then we took a look at the tweets. Okay, maybe this guy in Brazil is actually tweeting something about Taiwan, and that's more relevant. So it's a little bit complicated to assign a market or a country to a tweet. So we would like it to do a machine learning algorithm. And that's actually what we did here. So here you can see on the right the tweets, and we have assigned a market. And now the market developers, they're able to use dashboards and filter on the relevant markets and stuff like that. Okay, so that's one application. And general use cases are like automated customer service agents, chatbots in DCS. Will we see them? Maybe. Diagnostics and treatment systems like optimization of O&M in wind power in the Dungeons and Dragons lab. That's where we see the big value pool in Ørsted. Automated threat intelligence and prevention systems like in cybersecurity, in IT, so having algorithms look at logs, for example, log files, or the market abuse in trading that Umit talked about. There's a lot of use cases. And I call this a tangible introduction to machine learning, so I will just take a concrete example. And I hope you can follow, or otherwise please ask questions. You cannot do that on here, but yeah. So let's take a concrete example, and I have some data from a computer game that I'm playing. So let's take a look at the data. So we will just integrate it. So right now I'm reading the data here. Okay, so here we have the data. So the computer game is about riding a bicycle. So I'm riding on my bicycle at home against people all over the world. And we're participating in events like training rides, group events, races, stuff like that. And all these events are what you see here. So here we have a bike radar mission social ride. That's an event. Get fit together, blah, blah, blah. And I would like to filter these events by the event organizer to find high quality events to participate in. And that data is not available, so I've manually labeled it here actually by the organizer. So you can see here's an organizer like Bike Radar, here's VBR, here's Team MPI and stuff like that. And in the old days again, we would build a rule, and here it looks like there's an easy rule. It's just sort of the first word or words in the event description. But I've looked at data and it's actually more complicated. So it might be a good idea to train a machine learning algorithm to recognize the organizer of an event. So we have this data and it's labeled. So let's train a machine learning algorithm. The first step, there are some steps before we get to the machine learning algorithm. And that is to sort of split your data. That's good practice into training data and test data. So you train your machine learning algorithm on one set of data and then you test it on another. Never mix it. So the reason why I say that's because it's just the fundamental principle of training and testing machine learning algorithms. So I'll split the data I have into 50 rows of training data and 50 rows of test data. And then again, it's a computer, it's a machine. We have the data, but it's text data. It needs numerical data. So we will have to make numerical data. And also we need to tell the machine learning a little bit about what in the event description is interesting. That's called features. So we need to find some features. And I will start out by the organizers, getting that into numerical data. So here we've set up all the events. Again, we have 5 of the events here given by an ID. And then we have a label here which is numerical and understandable by the computer. And the one here identifies who is the organizer of the event. So Bike Radar is the event organizer of the first row, or the first event. Then we would take the event description, and select some features. What is important about the event in the description. And the features we're using is actually all the words we found in the event description. So here you can see some of them. In one event we found the word win, and in another winners and winning and wins and blah blah blah. So there's a lot of words. There's 1105 words. That's our features. And then we can count how many times these appear in an event. So we have a large table or matrix of all the events and all the features, similar to the one we saw for the organizer labels. So now everything is prepared. We have the pre-process in place. Then we can train. And now we have trained the machine learning algorithm. That was fast. So it's ready to use. And when we have an algorithm, we can use it to predict. So that's what we want to use it for. We wanted to say, okay, if I have an event, I want to label it with an organizer so that I can filter on quality organizers. So let's test how good it is. That we will do down here. So now we have an output here, and we can take a look at the predictions. So again, we have the input data like the event ID, the event description, and the organizer that I labeled. And now we have a prediction from the machine learning algorithm. And you can see here it could not find the organizer. We can go down and see, okay, here it selected a wrong organizer, and here it actually found the correct organizer. And actually, if we go down, we see that VBR it's capable of finding, and it's not really capable of finding a lot more. But I think there was one other organizer down here that it could find, like by radar. And in total, it's a lousy machine learning algorithm that we have for now. So it found 23 out of 50 events. That's less than 50%. That's not very good. But that's sort of an introduction to the process. So now we have a process that we can tweak and improve. And that's what you do when you train an algorithm. You set up a process or a pipeline, you get lousy results, and then you improve, iterate and improve. So now we need to invest to get the algorithm working. We need to do some iterations. We needed to train it on more data. 50 rows of data is not a lot to train on. We need 10,000 or millions of rows. We need to discover a better set of event features. We used all the words, and maybe that's not meaningful. Maybe we should filter some of the words out, or maybe there are other features we can find. Then we picked a particular algorithm. Maybe that's not a good algorithm. We would need to try something else. And there are some settings of the algorithms we can play around with. And for all of that, we need a data scientist, you could say. Somebody skilled in training an algorithm. But the important point is here we start with a lousy algorithm, and then we can iterate it, and it gets better and better. We can sort of easily get to 80%. 95% is normally expensive, and 99% is normally very, very difficult. But luckily it gets exponentially easy and cheaper over time. So all the things I've shown you, that you have to select features, you have to convert to numbers, you have to train, you have to pick algorithms and stuff like that, that'll be hidden for you in the future. It's just a service. You come with your data and your labels, and then it sort of does the magic for you. It's actually what is built into Excel today. You can play around with. Okay, that was it. Thank you.
Thank you very much. Thank you very much, Mark. I think we are a bit tight on time. I will try to continue without further ado. The final example is on improving the user experience. Some time ago, we were contacted by our colleagues in the robotics and process automation team who wanted to have some help sorting out thousands of emails Radius service desk receiving every day. This ended up in a machine learning classification algorithm which helps to sort out those emails. And this isn't considered rocket science so far, but this is a seed project towards something bigger. Imagine that every time you write to a customer service, you would get a personalized attention to your request. And it goes through no matter what time of the day you are contacting them. So just to give you probably some insights from the guy who actually ordered this. I want to play this video for you.
Being asked about why machines are important in the work that we do at our team, it's pretty obvious, as I have the privilege of heading our Robotics Excellence Center, and we automate processes for all of Ørsted. Looking across what we've done the past year is, I would say, consistency and quality of the output are the most common benefits, next to freeing up time to innovate and service our customers. One example of how we do that in our Robotics Excellence Center is when we have developed a robot. We document this solution, and sorry to say, to be fair to our developers, they would rather develop new stuff than they would spend time on documenting what they've done already. But having a good quality of the documentation is important when we want to shorten the time to fix a bug when it occurs. So we have developed a robot that actually produces this documentation. So once the comments in the code meet a given standard, then the robot can document it with no errors. Being asked where we can scale these solutions in the future, I think it's down to the way that we automate. We have applied or adopted the agile concept of producing a minimum viable product. So when we approach or are approached from areas in the business, we start out with a very thin scope. It could be a process, one product, one version of this product, and we automate the process end to end. And then as time passes, we add more instances to this process, we add more scope. We could probably take this process or this solution to the next area and very fast automate that one as well. In terms of which processes make sense to automate, every process can be automated to a given extent. Not everything, but a portion of it. It's a matter of how we eventually organize ourselves so that we can have a mail office to process some stuff in the work that we do, and then we can take over and finish what we set out to do. There are many reasons why we don't go full scale on AI. One of them is that I think everything is AI washed these days. We have AI in everything, and we may have statistics in many places, but AI or deep learning is not something that we go and use every day. The way that we approach a more advanced solutions than the rule-based versions is to look at what is needed and what data do we have. Very often we see that we know something is of importance, and we could probably classify this with an algorithm, but we don't have the data to actually do this. So step one is to produce the data, and once we have that data consistently, we can then add a model on top of that to produce the value. So there are certain steps before we can actually go all the way, and it's also down to quality and experience of us. We don't know that much, or we don't have that much capacity to actually spread AI all over Ørsted. I think we will see AI or statistics, deep learning, a lot of fun stuff, exciting stuff in many places within 1, 2, 3 years, but it will take time to go there, I think.
So Peter is saying that it's it will take a process. It's a lot to go, but I just wanted to give you a simple example. Recently, I started to use this artificial intelligence-enabled personal assistant. Her name is Amy. It's a robot basically, who is helping me to schedule my meetings. And here is the extract from our conversation with her, where she asks me that the guy wants to meet with me, and the only thing I say is actually find a spot in my calendar and schedule the meeting for me. And from there on, Amy actually is taking over, and she's getting me a meeting into my calendar. So if you think this is a commercial product and this is so difficult to build, then you should probably look at this one, because my colleague Christian from the innovation team, he has made this interesting project, small project, a demo, where he actually tried to look into all the data that we have on our meeting behavior. That means he took all the data that was coming from the calendars, and as a result of that, we could actually now predict what is the best place to meet. So let's say if I take Christian and myself, and I say that I want to meet with him for half an hour, and this should happen, for example, this week. Then, based on my patterns of booking the meeting rooms and availability, and Christian's availability plus his patterns of booking the meeting rooms, the system will actually recommend the best time and place to meet. And you can see it looks like Christian doesn't have that many meetings, and that's why his preferences are neglected. But my preferences are always in D1 3D or D1 somewhere. And this is the reason why it has actually, recommended to us. So, so this is actually happening right now, and this is something that everyone can go in and try to play with. So I would like to go on and try another video just for the matter of sealing the information that we saw right now. This is a DARPA competition back in 2015, and you can see that the robots were given very simple task of actually trying to either open a door or take a handle or go through something. And you can see these expensive robots, they are falling down, or they are making some awkward movements. And the reason I'm showing this is to make a parallel to what was just a couple of years ago, and how far actually the science in this area has gone, especially using artificial intelligence. Because as we mentioned in the beginning of the conversation, artificial intelligence is used to make robots be better at exploring the environment, right? So this one is the final one, the final fail. Now look at this guy. The guy doesn't care whether it's what kind of terrain it is, if it's slippery or not slippery. He's just determined to go through to the goal. This guy, he doesn't even need the legs. He can walk. He can roll on his wheels and be very fast and agile in his movements. So. And also, when it comes to the terrain, it doesn't really matter for him, because you'll see now that, for example, this one, and this is the final one that to show that parallel, where from the point where the robots could not even open the door, now look how determined he is to open the door, he or she. I don't know how we call the robots now. Robot. Yeah. There you go. Yes. And now this one is happening on the Earth. Look what the guys made in space made. To show the full potential of advanced analytics, artificial intelligence, robotics, IoT all together. To finish my presentation, I would like with a short story which is near and dear to me. And this is my father. Back in 60s, he was part of a scientist group who was experimenting on the parts of the rocket the USSR had to send to the space. He worked there for many years, and it was a huge investment. There were more than 100,000 people involved. It has been a top secret project. But on the other side, I have Max. This is my friend. This is my classmate from my school back home, who is actually a lead propulsion engineer at SpaceX, who had to fly this Falcon Heavy, and he was not flying it. That engine that he was projecting was flying it. So he is on the other side of this picture, and the idea is that within this last generation, there has been such a leap in technology, and now we are sitting here and talking about artificial intelligence and speculating whether it's next 5 years or whether it's next 10 years. The idea is that even shallow representations of artificial intelligence is adding value throughout the value chain, and it's real and it's applicable already today. And Advanced Analytics team in IT at Ørsted would like to help any business to take this artificial intelligence journey. Thank you very much for your attention.